With a BS degree from California Polytechnic University, Mr. Cornell has worked in the reciprocating pump industry for more than 35 years and is a member of the Hydraulic Institute and the American Society of Mechanical Engineers.
So we're going to have a little discussion about acceleration head. Now, acceleration is the change in velocity. And we can see this in basically a pulsation curve, which is a sine curve, a modified sine curve, depending upon the type of pump used in piston, in diaphragm, even in the rotating peristaltic pump. A given amount of liquid is captured and then expelled. Well, what happens in that process is, if you think about a piston, it pulls back to charge on the inlet stroke. And then on the discharge stroke, it starts moving through the chamber and pushing liquid out. In the initial phase of that movement of the piston, there's no flow. But the flow starts and builds or accelerates, if you will, through the stroke until it reaches midpoint. And then the flow starts slowing down till you reach the point where the piston and the diaphragm pulls back and recharges on the inlet stroke. And the flow, depending upon the type of pump, can actually stop momentarily. Well, this curve is not only a flow curve, but it's a pressure curve, because at the start of the stroke, there's no pressure. Pressure builds to the midpoint and then starts reducing down as the flow decreases through the stroke cycle. Okay? Now, pressure also creates the vibration and other components that occur during the stroke cycle. Vibration, all the other elements. For that pulsation, we use a pulsation dampener. But when we start talking about acceleration head, it's the energy, from our point of view, required to accelerate or change the velocity of the liquid in the system from at rest or zero to some point in the cycle. Now, a race car, for example, starts out at zero, accelerates to a maximum point through the lights, and then stops, decelerates. It would, in effect, be a similar type curve. All right? Well, relating to our situation, it takes energy to move that liquid or accelerate that liquid. Okay? On the discharge of a pump, it takes that energy to accelerate or move the liquid down the pipeline. Okay? Think of an analogy of a freeway system and the freeway going to a large city. The freeway has a bypass around the city. Okay? If you take the bypass and hold your speed at a steady speed of whatever, 60 miles an hour, you're going to use a certain amount of energy. Remember Newton's law about a body in motion tends to stay in motion unless acted upon by an opposite or equal reaction. But if you get off the freeway and decide to drive through town and hit every single stoplight, now you're decelerating and then re-accelerating, then decelerating, then re-accelerating. That takes a lot more energy or more gasoline than if you stay at a steady speed driving around the city. Now the point of this is, and we're going to talk about the discharge side of the pump, but also the inlet side of the pump, but the point of this is, and as an aside, just remember when we're talking to people that all friction charts that are published, which is a pressure loss per typically 100 feet in a pipe, are based on steady state flow. Okay? Centrifugal flow, if you will, like out of a faucet. In other words, once you get the liquid moving, it stays constantly moving, takes less energy once it's moving. When you start a centrifugal pump, there is a peak of power used to initially get the liquid moving. Then that peak energy drops down to an average flow. or average energy use as the product's flowing. But with a reciprocating pump, that flow is not constant. So if you try to use those pressure loss charts that are published, it would not relate at all to the energy required or the loss due to friction created by a reciprocating pump, right? Because we are starting and stopping the flow just like going through town. So if you take a pulsation dampener and put it at the discharge of the pump, and there could be a pump. On the discharge stroke of the pump, a certain amount of liquid goes up and is accumulated into the dampener. Remember, there's a gas charge on the top side of the dampener, but it's always at a lower pressure than the system pressure. So a certain amount of liquid goes up temperature into the dampener. Now that takes some energy to push up against this resistance. But when the pump reaches its peak and starts to stop, or at the end of its stroke, and retract to recharge, now the pressure in the dampener is higher than the system pressure, so this accumulated or stored liquid is pushed back into the system by the stored energy that the pump provided, and it evens this flow so that we don't have a peak or a valley, but we tend to have near steady state flow like that produced by a centrifugal. Well, when the system is in near steady state flow, we are not using excessive energy, okay? We're using the pump's energy, but we're not losing it. We're just storing it momentarily and then reintroducing it back into the system. It's relatively easy on the discharge of the pump to overcome acceleration head or deal with it, because you've got the power of the pump, whether it's compressed air or a motor or whatever form of energy generation is attached to the pump. So that even if you don't have a pulsation dampener, you have the power to do it. It takes more energy, but you have the power to do it. Where we can have problems is on the inlet side of the pump. Because now that acceleration head can work against you, and you only have atmospheric pressure as the form of energy or power on the inlet side of the pump. Remember, the pump can't do anything until a liquid gets into it, and it applies its energy at that point to discharge it. But up to that point, all we have is what? At sea level, 14.7 psi. Okay? Now, what's important about that is that if we end up with a relatively long inlet system before our pump, we don't have to go back to that friction loss chart. Remember, we talked about steady state flow versus reciprocating or start-stop flow. Okay? So the pump is going to create a low pressure area, assuming that we don't have a lot of inlet pressure. It's going to create a low pressure area. Atmospheric pressure, whether it's a tank or whatever, is going to push the liquid into the pump. Okay? But it has to overcome this friction loss. In other words, every time this pump shifts, remember our sine curve, every time this pump shifts, not only does the flow slow down on the discharge side, but the inlet valves close and the flow slows down and stops, depending on the number of pistons in the pump, stops on the inlet side. Now, you got to re-accelerate that flow, right? On the discharge side, we're pushing it with energy, but now we've got to restart that flow. In loose sense of the word, it's coming in slugs. Well, if you have a lot of friction loss, you're going to lose flow because, remember, we've only got this 14.7 pounds. If we were to install an inlet stabilizer here, And in some cases, depending upon that inlet pressure, actually put a vacuum in this. When the pump's valves close, this liquid is starting and stopping, but it will accumulate on the inlet stabilizer, provide a ready source of product or liquid right at the pump's inlet, so that during the shift, when this flow slows down, we've accumulated liquid in the accumulator or the inlet stabilizer. So the pump then, when it shifts, pulls this liquid out of here. It's not having to re-accelerate the whole line. Takes less energy. Ensures that there's not cavitation, ensures that we get full fill in each of the chambers, and it's particularly important on multiple piston or multiple diaphragm pumps. And I said, depending upon what the conditions are, we may actually pull a vacuum in the dampener. The idea is when these valves close on this pump, this flow, instead of stopping altogether, cycles up into here, keeps in motion like the car going around the city on the freeway, so that there is less energy expended when the pump shifts and the inlet valve opens to the chamber. Now, another scenario that can happen is that we have too much positive pressure going to the pump, okay? Now, because of the acceleration head and the pressure involved, when the valve closes, we create water hammer. And all water hammer is a change in velocity or a change in acceleration, typically rapidly, okay? And that occurs when this valve ball closes, but the product is moving because there's acceleration. We have a force, which is the liquid, created by the mass moving and its speed. That force wants to go somewhere. It can be fairly significant depending, again, on the conditions, and when the valve ball closes, that force is created. It can damage components and pumps, it can damage gauges, it can damage gaskets, flanges, threaded joints, can cause all kinds of problems because that pressure spike can be 4 to as many as 8 times greater than the flowing pressure. Well, now we charge this inlet stabilizer different, and it acts like an accumulator and stores that energy much like it does on the discharge side. So that when the valve balls on the inlet of the pump close, instead of this liquid continuing to move because it's under acceleration, slamming in the check valve and creating a big pressure spike, now the inlet valve balls close, the liquid is cycled or accumulated up into the dampener. The acceleration is decelerated at a controlled, slower speed, so no pressure spike occurs. And we've accumulated liquid again right here, so that when the valve ball opens on the inlet stroke, liquid is immediately available, and this stays in motion. Now, we have effectively changed this acceleration head, whether it's loss or pressure, into steady state flow at a constant pressure and a constant energy requirement. Okay? So the whole point is to change this reciprocating flow, and it's either gain or loss from acceleration head into a constant steady state flow, so that we eliminate the problems created by this acceleration head. Now, there are formulas that allow you to calculate both pressure and flow loss and energy required to overcome the resistance to flow of the acceleration head, so that you can properly size the piping and elbows and all the other components in the system to maximize efficiency and minimize the use of energy. Okay? But many people who do these calculations to ultimately determine what the total dynamic head of the system is, Total dynamic head basically is all of those components, the friction loss, pipe size, elbows, all the other things, to determine what size pump is needed to produce the flow at the discharge pressure required. If you don't use inlet stabilizers and pulsation dampeners, you can't use a key component of that formula, which is the friction loss created by the steady state flow in the pipe. So you can't use those charts. You can use acceleration head components and bring that in the equation. But with the installation of inlet stabilizers and pulsation dampeners, you can just basically go to the standard friction loss charts and use those, and they will be accurate. In addition, obviously, to minimizing the energy use, we're going to protect, again, system components, gauges, valves, flanges, any other components in there, diaphragms, and the components in the pump. The inlet valve balls, the diaphragms, all the various other components that would receive shock, or in the case of cavitation, the damage caused by the collapse of high pressure energy when it hits the piston face or the diaphragms in the pump. So it can be rather complicated, but it can be reduced down to relatively simple proposition and calculations if we just have everybody understand what this acceleration head or force is and how to minimize it or maintain it or control it. In order for the inlet stabilizer or the pulsation dampener on the discharge to control or minimize acceleration head, it must be properly located. For example, the inlet stabilizer is going to handle this acceleration head up to the point where the dampener is installed in the system. Not between the pump and the dampener, but from the beginning source of the liquid to the dampener. So if we move the dampener here, for example, everything from here on is going to have this acceleration problem because the valve is opening and closing and affecting this length of pipe flow. So this needs to be, the inlet stabilizer or the dampener needs to be installed as closely as possible to what is causing this acceleration head loss or positive pressure, okay? So we recommend within 10 pipe diameters of the pump's inlet or 10 pipe diameters of the pump's discharge. But it can't be effective if it isn't acting on the full flow volume of the liquid in the system, okay?
Size, location, and charge.
Size, location, and charge is exactly what's required, not only to minimize pulsation, but to control and reduce acceleration head. In effect, with the inlet stabilizer or the pulsation dampener located within these 10 pipe diameters, okay, we have eliminated acceleration head. You're going to totally eliminate all of it, but we have eliminated the majority of it to the point where it no longer has to be a consideration. Okay, on the inlet side and everything past the dampener on the discharge side. We are in effect have turned this into this. You'll see it if you look at a pressure gauge at the discharge of a reciprocating pump. Because at this point of peak acceleration, the gauge may be at 100. At the valley, depending on the type of pump, the number of cylinders or pistons, the gauge may be reading 20. But when you've minimized or eliminated acceleration head, and we have this flow, you'll reach a steady state, again, depending upon the type of the pump, number of cylinders, somewhere in the neighborhood of 40 psi. That's the true number that you would get if you size the system and figure the total dynamic head using the friction loss charts on a centrifugal pump. Okay?